Hello everyone, in this tutorial I'm going to show you how to perform a buckling simulation in Abaqus. Buckling is characterized by a sudden sideways deflection of the structure member, and the structure will remain straight for a load less than the critical buckling load. And so the critical buckling load is the greatest load which causes this lateral deflection. So we're going to perform this on a very simple example that we're going to have a column with a cross-section of circular cross-sectional area, and with a radius of 7.5. We apply a force from the top, and at the bottom is fixed. But before doing this in Abaqus, I would like to show you how to do a hand calculation to find these critical parameters. So the first thing is to find the moment of inertia. As you can see, this is a formula for a circular cross-section area. And then we find the cross-section area for it, and also we know that we know the Young modulus, which is this one is for still 2 times 10 power 5 megapascal. We know the Poisson ratio, we know the yield strength, so we can calculate a critical buckling load. That is a Euler formula, and by substituting the numbers to this formula, we will have the critical buckling load as 3,400 Newton. So there is a factor here, which is a K factor, and this K factor will basically, based on the structure that you have to select this theoretical K value. So as you can see, ours is this one, so we only have a fix at the bottom, and at the top it can move to the left or right. So the K value for that is 2, and so I mean, depends on the condition of the structure. We'll select these K values. So again, this critical buckling load is something that you have to learn in the first year of engineering course at university, and so if you haven't learned it yet, it would be good to look into literature about this and how you can find these values. And obviously the aim of this tutorial is more about the software, so we're going to quickly pass through a hand calculation. So after finding the critical buckling load, we can find the critical stress, which is equals to critical buckling load divided by area. So it's basically force divided by area, and we'll find this value as 19.25 megapascal, and the maximum deformation equals to critical buckling load times the length of the column divided by cross-section area times Young modulus, and from here we'll find the maximum deformation as 0.0579 millimeter. Okay, now let's start modeling this simple 2D wire beam in Abaqus. So I'm gonna create a part, and there's gonna be 3D deformable wire, and the unit is in millimeter, so that's gonna be thousands. And I'm gonna just draw one straight line. This is very simple geometry. So, and from here to here, that's going to be 600. And so I'm going to cancel these, click on OK. So that's going to be our a simple 2D wire column. And then in property section, we have to create a material property for this one, which is in this case is going to be steel. So I'm going to type here steel, and this one is going to be elastic 2E5. And so again, this is in megapascal, so we have to make sure that we are putting the correct unit system here. Poisson ratio 0.3. Click on OK. Next step is to create a profile for this one. So I'm gonna click on create profile. It's going to be circular. Click on continue, and the radius let's put 7.5 millimeter. Click on OK. Now create section, beam, continue, and select this one. Click on OK and assign this to this line. Click on OK and done. And then we assign a beam section orientation. Click on done and press enter and OK. And so now if I go to view and part display option, render beam, we can see what we have here. So deactivate render, and next step is assembly. So I'm gonna import this one, and we are done with assembly, and now we need to create this step. So here is it's going to be a difference comparison to previous example. If you remember, in previous example we're using a static general, but in this case we are going to use a buckling, which is to find the critical buckling load. And so here what we have here basically simply we have two different methods, and blank source method is generally faster when a large number of eigenvalues is required, and subspace one may be faster when only a fewer or less than 20 eigenvalues are needed. Then we have a vector use per iteration, and this number is usually determined by Abaqus standard, but can be changed if you want. And normally if you increase this number you might have a better convergence and faster when you use more vectors. And generally you can get the value of this vector using this formula n+8, which n is the number of the requested eigenvalue. So number of the eigenvalue requested, basically the minimum is 1, and you can request as many as you want, but generally the first eigenvalue is the critical one, is the one that will create a will cause a buckling basically in the structure. And also we have a maximum number of the iteration here, that again the default value is 30, but again you can increase this value if it's needed. Generally buckling analysis is quite fast, so you normally get if you request like 1 or 2 eigen values, you only need 1 increment generally. But if the 30 value is not enough, then you can increase this one until you have a convergence and you have a result basically. Okay, so in this case I will request 2, and I'll keep this one as it is. Click on OK, and if you look at this one, basically Abaqus added this value 4, so when I put 2 here, it put a 4 vector for per iterations. So now in traction I don't need to do anything here, and in load section I'm going to apply a displacement. So I'm going to fix the bottom one, click on OK, select the bottom one, and for the top one I apply a load, so it's going to be concentrated load, and click on this one, click on OK, and here this one is going to be 0, this one is going to be 0, and this is going to be negative. So the value that you put here is basically whatever you put here at the end, you have to times that by the load factor that you get at the end. To clarify this, I will start with 1. So if I put a value of 1 here, what I'm going to get as a result is going to be my critical buckling load, because if I times that by 1, then that will be equal to critical buckling load. So I'm going to run this simulation once I have a value 1, and then I will just put a random force, then we will see the difference, if there is any difference actually. So let's make this one -1. So as you can see, we are applying a buckling displacement in compression. Then in mesh section, apply a mesh, assign a mesh to this spot. Let's see how coarse. So 60 is coarse. Let's make it 20. 20 is not too bad. So assign this mesh, say yes. Now I'm going to job section, and let's just create the first one. Before creating that, I'll just rename this, and I will just call this one 2D buckle. And I'll just do the same, so 2D buckle number 1, click on OK, and let's submit this one to see if any error we're gonna get. So I'm gonna monitor this one. So as you can see, 1 increment, the job is done, and I can see the result. and as you can see the eigenvalue value is 3406.5. Let's compare to the hand calculation what that will be calculated. So as you can see, the eigenvalue, the critical buckling load is 3400. So in this case, what I applied was 1 Newton. Let's see what will happen if we apply, so if I go to load, if I apply, let's say minus 800, and I can submit this job. Let me minimize this. So again, monitor this. The job is done, and I'm going to show you the result. And as you can see, the value here is 4.25. And so if you remember, what the value that I applied was 800. So if I times 800 times 4.2581, that equals to 3406.48. So it doesn't really matter what you apply there. What you get here is basically a load factor, or is we call it eigenvalue number, and you have to times that to the applied force. In my case, when I started this video, I applied -1, so the value that I got was 3406, which I times it by 1, it's going to be the same. So as I showed you here, if you apply 800, and what you get here is 4, and once you times that, you get exactly the same value. So now in the next step, I'm going to show you the linear post-buckling simulation. So get a copy of this one and just add static in front of it. Click on OK. And what I'm going to do, I have to replace this one. So this was step that we had. So I can right click on this one and click on replace. And I'll say, instead of buckle, I want to have a general, and instead statics. Click on continue. Okay, so keep this one as linear, make this one 0.1, and this one 15, and this one 1000. Click on OK. And in the load section, I can edit this one. So if you remember, the value that we found there was 3406. So this is what is a critical buckling value. So if I put this one, I want to see what is going to be the maximum stress in the maximum stress and displacement in this column. So click on OK, and let's see, the mesh is all right. Just double check to see that if the element type is correct. So select this one. So as you can see, it's on beam. Yeah. So I'm going to minimize this, and going to type to the buckle, the static this time, and click on OK. Continue. OK, and then submit this job, and let's see what we're going to get as a stress value. So I'm going to first monitor this one, but the job is already done, so there wasn't any error, and it was a very fast simulation because the geometry is very simple. So show the result, and so as you can see here, the stress value is 19.27 megapascal, and let's see what we found. So as you can see, very close to a hand calculation one that is 0.25, and now we can find about the maximum deformation, which is 0.0579, and let's see what we got there. So here is 0.0578. I think that they're very close to each other. Yeah, so this is 578, this is 579. So as you can see, the values are very close, and we basically could verify a numerical model using the hand calculation. Also, I'm gonna quickly after this one show you how we can do this one in 3D, and you're gonna see that the 3D result is not gonna be as close as 2D wire result to a hand calculation. Okay, now I'm going to generate a new model, and I'm going to call this one 3D buckle. Click on OK, and so create a part. So it's going to be 3D solid, and the size, we don't need it to be this big, just 200, because we're going to draw a cross-section area and then extrude it. So click on continue and draw a circle and give a dimension to this one. The radius is 7.5, and then click on done and extrude this one 600. So we have this, but if I go to mesh section, you see that it's yellow, and if I want to apply the structure mesh, I have to basically create the section, and I will do that here. So by offsetting that datum plane, so I'm going to offset the YZ one, so this is a YZ as you can see, and I'm going to offset it 0, which is going to be in the middle, and also XZ, which is this one. Again, I'm going to offset this one 0, so it's going to be in the middle. And then I'm going to create a section cut using a datum plane. First, I'm going to select the top one, and then I'm going to select both of them and click on OK. And then this one, create partition. So now if I go to mesh section, you see that it's green, so I can apply a structure mesh to this one. So we are done with this one. I'm going to go to property, similar to the previous the 2D example. I'm gonna create a still elasticity elastic, so this is gonna be 2e5 and Poisson ratio 0.3. Click on OK. Here we don't need to create a profile because we already have a profile, and so it's going to be solid, homogeneous. Click on continue, and still click on OK, and assign this one to this geometry. Click on done. So we are done with this. In assembly, I import this one as a dependent, mesh on a part, and then step, I'm going to create again the buckle. Click on continue, then I'll request a 2 and keep the parameter as default, because again this is a very simple geometry, so with we don't need more than 30 iterations. Click on OK, and interaction. So in interaction, what we can also do, we can actually apply create a coupling to that a specific point. So let's do this one as well. So if I offset this point, so maybe I keep that one as a yeah, so I'll fix the bottom one. I'll apply a load to the top one. So let's just offset this one, as offset this middle point, and it should be in a Z direction. So I'll do 0 0 10, and I'm going to couple this one to this one. So coupling, and I'm going to select so before coupling I have to give a reference point to this one, otherwise it's not going to work. So again, coupling, select the reference, click on OK, and node region, select these 4 areas, click on done, keep the parameter as it is, click on OK. So this is the cup, so I can apply my concentrated load to that specific point. And then so now in a load section I can apply a load to this point, so concentrated force, click this one, and so it's going to be 0 0, and that's going to be -1 because it's in a Z direction. And then I will fix the bottom one. So so rotate this one, go to here, select the first one, select 4 faces by holding a shift, click on OK, and select this. So that's fixed. And then next step is to basically apply a mesh. Go to mesh section and go on a part, so this is green, and select everything, click on OK, and apply 2 and assign a mesh. So the 3D analysis is going to be mesh sensitive. So if you have, for any reason such as like not using educational license, you have to apply a coarser mesh because you're limited with 800 nodes, then it's possible that you are not gonna get the accurate result, because the 3D result, as I said, is very sensitive to mesh. So in the here, create and 3D buckle, and submit this job. So I can monitor this to see if there is any error. There's not, and see we have to wait for the buckling result. So this is done again with a 1 increment. It was a fast one, so I can show the result. And as you can see, the buckling value is slightly lower than what we found in at the 2D analysis, and as you can see, it's 3277, so slightly lower than hand calculation. And I can tell you that if you so what we can do, we can go to mesh and increase the accuracy of the mesh. So if I select this one, and instead of linear I use quadratic, so I'm going to, instead of linear order, I'm going to use the quadratic, and I get rid of this reduce integration and click on OK. So that means that we have more nodes for Abaqus to calculate the equation, basically. So I'm going to submit this one and see that if this is going to affect the result. So I'm going to monitor this. So it might take longer than the previous one because we basically using a quadratic order, and we got rid of the integration. I'll explain all of these in the mesh section. So if you haven't watched that the video in the fundamental section, please go back and watch those videos. Okay, the job is done, and I can see the result. So as you can see now, the eigenvalue is 3401.9. So as you can see how sensitive is to 3D result to the mesh quality. And in a 2D simulation, even if we're using a much coarser mesh, we would have still got a value around 3400. But as you can see in the 3D result, although we have a very quite nice structured mesh, however, when we have these let me just show you here. So when we are using a linear and a reduced integration, as you can see, we reduced the accuracy of the result for the eigenvalue simulation. So you have to be careful of the 3D results. You have to definitely do a mesh study to see that if your mesh will actually affect the result. Obviously, for a complex structure, there is not a hand calculation that you can actually compare your 3D result with a hand calculation to see that if your mesh is appropriate. So in those cases, what you normally do, you normally have to do a mesh study to see that if your result is mesh sensitive. In that case, then you have to work on your mesh so the result is not going to change by changing the mesh size. And obviously that needs a time, and sometimes you need a big computational power to solve these like a complex geometries. So let's do the same thing for the static one as well. So I'm going to just copy this model. I'm going to call this one static, and I'm going to go to step, replace this. So general static, click on continue, and I'll make this one 0.1, this one 15, and this one 1000. Click on OK. I just forgot what was the value for the buckling, so I'll just double check that. So 3401.9. So I'm gonna go to static one in the load, and I'm gonna change this one to minus 3401.9. Click on OK, and now I can create a 3D buckle, one static, and click on OK, and save this one. I'll save it later, so I'm going to just submit this one. So again, because we have much coarser and finer mesh, it would definitely take longer to solve it in comparison to the coarser mesh. So that's why the mesh section is quite important, especially when you have a complex geometry, and you have to spend enough time on mesh. So you actually make sure that first your result is accurate and you're not wasting the time when you're solving a problem, because if you have a too fine mesh, then you're basically using a lot of resources and a lot of time which is not actually necessary. So I'm going to just pause the video because this one will take a little bit longer than the other one, and once the result is done, I'll show you the result. Okay. The simulation is done. I'm going to show you the result. So as you can see, the stress value is slightly higher than, so the stress value we have to ignore these high values. As you can see, the high value is only at the bottom here. And as you know, in the 3D result, 3D simulation, when you have the sharp edge, you have a singularity point, and those are area basically that you have a higher stress. But we can actually find the stress value in this part of the beam, which is going to be more close to our hand calculation. So if I use the probe value, and if I go to node, so if I use these nodes, you see that the stress is like around 18.7, and so if I use this one very close to, so maybe here, so as you can see 20.16, we ignore basically this high stress that is created here, and this is basically a problem in a numerical simulation problems. Even if I use a finer mesh, so if I decrease the size of mesh, you'll see that this value will increase. So so kind of, in order to get rid of this, what we can do, we can apply a small fillet in the corner, so to get rid of this sharp edge and the singularity point. So if I choose this value around this area, so the nodes, because I have a quadratic one, so as you can see I have one in the middle as well, and as you can see the value is around 2.16, so here is 18.25, so quite close to a hand calculation, but it's not as close as a 2D analysis. Now we can actually check the displacement as well. So the displacement value is 0.0576. So as you can see, the displacement value is very close to a hand calculation, but the stress value is not. And the reason is that the stress is mesh sensitive. So the size of the mesh, your geometry, as you can see, for instance, having this sharp edge will affect the mesh result. Sorry, affect the stress result. So in this case, our stress value is not as close as the displacement or eigenvalue values in comparison to a hand calculation. So this is the end of this tutorial. I hope you enjoyed it and you learned about eigenvalue, and I hope to see you in the next video. Thank you so much for watching.